Hello everyone, welcome back to our channel. This is Anana Kumar Singh. Today we are going to discuss a very interesting topic related to metric space. Hope this topic will catch your great interest and this problem is very helpful to you in your further studies. Okay, let's go and solve the problem. If D maps R cross R to R be a function, if D maps R cross R to R be a function on R such that D of x comma y is equal to mod of x minus y for all values of x comma y belongs to R, then so that D is a metric on R. We have given that D is a function from R cross R to R. It is given here. And what we have to prove? We have to prove D is a metric on R, where R is the set of real numbers. So before going to prove D is a metric, we have to recall the properties of a metric. And we also familiar with that there are four properties to form a metric. If D satisfies all the four properties, then it is said to be a metric on R. So we will do it step by step to show D is a metric on R. It is given that D maps R cross R to R such that D of x comma y is equal to mod of x minus y for all values of x comma y belongs to R. The first property is D of x comma y is greater than or equal to 0 for all values of x comma y, which we need to show first to say D is a metric. Okay, so from the definition of D, it is given that D of x comma y is equal to mod of x minus y. Since mod of x minus y is always greater than or equal to 0 for all values of x comma y belongs to R, this implies that D of x comma y is also greater than or equal to 0 for all values of x comma y belongs to R. As we know that modulus function is always either greater than 0 or equal to 0 but never be negative. So here we can say that from the definition of D function is D of x comma y is equal to mod of x minus y, from where we can say that mod of x minus y is greater than or equal to 0 for all values of x comma y belongs to R, from the property of a modulus function which suggests that the function never be less than 0. So here we can say mod of x minus y greater than or equal to 0, which implies D of x comma y is greater than or equal to 0 for all values of x comma y belongs to R. So the first property to form a metric is satisfied here. Now let's go for the second property. The second property is if D of x comma y is equal to 0, if D of x comma y is equal to 0, then it implies that x is equal to y, and if x is equal to y, then it implies that D of x comma y is equal to 0 for all values of x comma y belongs to R. And this is our target to show D is a metric. Now for this, let's take the definition again. X minus y, mod of x minus y is equal to 0. We should take D of x minus y, x comma y is equal to 0, which implies that mod of x minus y is equal to 0. As we know that D of x comma y is equal to mod of x minus y, which again implies that x minus y is equal to 0. As we know that modulus function is equal to 0, it's only possible when if x minus y is equal to 0. If mod of x is equal to 0, it suggests that x is equal to 0. So from the definition of modulus function, we can say that mod of x minus y is equal to 0 implies that x minus y is equal to 0. From where again x is equal to y. So if we take D of x comma y is equal to 0, if we take D of x comma y is equal to 0, then we will get x is equal to y. Conversely, if we take x is equal to y, then it will implies that x minus y is equal to 0, which will again implies that mod of x minus y is equal to 0, which will again imply that d of x comma y is equal to 0. So d of x comma y is equal to 0 if and only if x is equal to y for x comma y belongs to R. So the second property to form a metric is also satisfied here. Let's go for the third one. The third one is the symmetric property. For d of x comma y, we have to show d of y comma x. D of x comma y, it will be equal to d of y comma x, the symmetric property. And for this, we start from here. Let d of x comma y, which is equal to mod of x minus y, for all values of x comma y belongs to R. Now mod of x minus y, which also can be written as, if we take minus outside as common, then we will have minus under the bracket y minus x, close the modulus. And as we know that mod of negative x is equal to mod of x, so from the property we can say it equal to y minus x modulus. And from here we can say, as d of x comma y is equal to mod of x minus y, so mod of x minus y is equal to d of x comma y. So if we take mod of y minus x, then it can be written as d of y comma x, d of y comma x. So guys, d of x comma y is equal to mod of x minus y, which is equal to mod of negative of y minus x, which can be written as mod of y minus x. And from the definition of d of x comma y, we can say mod of y minus x is equal to d of y minus y comma x for all values of x, y belongs to R. So the symmetric property is also satisfied here. The symmetric property is d of x comma y is equal to d of y comma x. So the symmetric property is satisfied here. Now the only remaining property is the triangular property, to say D is a metric. Let's go for the fourth property, which is known as the triangular property. And what is this property? If we take 3 points x comma y comma z belongs to R, then this property states that d of x comma z, that is distance from x and distance from x to z, is less than or equal to d of x comma y plus d of y comma z. Now this is our target to fulfill, and from the definition d of x comma y, d of x comma y, it is given that x minus y's modulus. Let us take 3 points x, y, z belongs to R, and we have to show d of x comma z less than or equal to d of x comma y plus d of y comma z, to say that this satisfied the triangular property also to form a metric. So our target is this: d of x comma z, it is equal to mod of x minus z, which can be also written as mod of x minus y plus z, x minus y plus y minus z, which can be written as x minus y mod of x minus y plus y minus z. Now a very familiar property of modulus function, as we know that if we take mod of x plus y, then we know that it is lesser or equal to mod of x plus mod of y. It is a well-known property of modulus function. So we can say from here that if we take x minus y as x and y minus z is as y, so it can be written as lesser or equal to mod of x minus y plus mod of y minus z, which is equal to mod of x minus y. It suggests that d of x comma y, and mod of y minus z, which is equal to d of y comma z. So Altogether we can say that d of x comma z is lesser or equal to d of x comma y plus d of y comma z. What I have done, d of x comma z, which is equal to mod of x minus z, it also can be written as mod of x minus y plus y minus z, which can be break as mod of x minus y taking together and y minus z taking together on the other side, which can be written as lesser or equal to mod of x minus y plus mod of y minus z by the familiar property of x plus y modulus is lesser or equal to mod x plus mod y. So from here we can say that mod of x minus y is equal to d of x comma y, and mod of y minus z, which is equal to d of y plus y comma z. So altogether we can say d of x comma z is lesser or equal to d of x comma y plus d of y comma z. At last we have reached at the bottom of the fourth property, and altogether we can say that all the four properties are satisfied here for D to be a metric on R. Since D satisfies all the four properties to form a metric, so we can say D is a metric on R, and this metric D is called usual metric. Usual metric on R. This metric D is called the usual metric on R and denoted as du. Denoted as du. The metric D, the real number set R with the usual metric D, is called the usual metric space. So guys, D is said to be here. The usual metric on R is frequently denoted by D suffix u, and the set R with the usual metric D is called usual metric space. Okay guys, if you like this video, please support us. Okay, bye bye.